concluding the unit hydrograph, and we're introducing the concept of routing. And once we have the ways of handling routing, we will have covered all the pieces needed to effectively use a modern hydrologic model for asking research and engineering questions about a watershed. So routing is the term that refers to simulating the movement of a discharge signal through reaches. Reaches is a jargon term for streams or engineered channels, or basically flow pathways. And the routing process accounts for storage within the reach as well as any flow resistance along the travel path. And so what its benefit is from a hydrologic perspective is it allows explaining the behavior of a basin that's comprised of interconnected sub-basins. So if we have a situation where we can identify within a watershed sub-watersheds that are somehow meaningfully different from each other, but they're interconnected as part of the whole watershed, routing gives us the ability to consider that situation directly as a collection of interconnected subbasins. So there's two generic types of routing, referred to as hydraulic and hydrologic. They're doing the same thing, but they behave and work quite differently. Hydraulic routing uses the continuity equation and momentum and aspects of an energy equation to account for friction. Collectively, they're called the St. Venant equations, and that would also be called full dynamic routing. And these hydraulic routing is implicitly a component of the open channel flow class. Now we will examine next week use of SWIM as a hydraulic routing tool, but not in the same detail you would get in the full open channel flow class on that effect. Hydrologic routing instead just uses the continuity equation. Or another way to picture it is it uses a St. Venant equation with the inertia terms ignored and what's the other term? Inertia terms and convective acceleration terms are neglected or assumed negligible. Hydrologic routing, although it seems to use a simpler approach, is certainly has utility and application in many instances. So it's worth discussing. So routing expressed in one context is expressed in this slide. Imagine you have a hydrograph at one location. We'll call that the inflow location. You have some understanding of the reach characteristics, so geometry, frictional understanding, so that we know that the storage in a reach or a hydrologic element is some function of the inflow and the outflow. And what we want to know is what the hydrograph looks like at the outflow. If those conditions are met in your questioning context, then you have what's called a routing situation. The reach can be a channel, a river, a reservoir, or some other similar feature. A reach, by convention, is not going to be an overland flow path. It's after the water has either channelized or collected in some sort of storage element. That's an important distinction because if that were not the case, we could create unit hydrographs for a channel, which one could still do, but that would be absurd. You can make the numbers work, but it'd be extremely hard to mentally wrap your head around what's going on. So here's a picture that's depicting some of the ideas that are involved in hydrologic routing. So here we have an upstream hydrograph, which is this guy. And I'm going to go ahead and I'll draw on it with a pen. And I want my hydrograph to be, cyan. It's almost teal. That maybe not such a great idea. There's our upstream hydrograph. And some distance, that's supposed to be a big teal line. And we'll get my downstream one into yellow. And then a distance downstream. So imagine this occurs at one location, and 17 miles downstream of that location, we observe this hydrograph, which is on the same flow element, same river, same channel, same drainage ditch. So a 17-mile drainage ditch would be a pretty good-sized drainage ditch. So there's our downstream hydrograph. The distance in time between the two peaks on this drawing is the travel time. The change in height in the two peaks is called the attenuation. So it's how much the peak discharge is reduced by having to travel, an hour to get to the new location. And the attenuation can be explained in a couple of ways. Certainly friction plays a role, but more importantly, that hydrologic element, can think of it as a long, slender bathtub. It has storage, so water that would otherwise appear as discharge has to be stored in order to transfer the remaining water on downstream. And the details of that are dependent on the analyst's choice of what kind of routing method to use. So if we examine the behavior of these hydrographs over a relatively short time interval, here shown as delta t, and at a little bit before delta t and after delta t are shown here by these lines, and then here's this increment exactly at the timeline of interest. The difference in ordinate height between the inflow hydrograph and the outflow hydrograph is how much is in storage in the routing element, the reach, if you will. And then we get to this time unit right here. So there's inflow rate, there's storage, and then there's the portion that's contained in the downstream hydrograph. And then we go a little bit further in time, and this red bar also represents the storage, but it's at a different time interval. So this red bar, the one on the right, if we subtract from it the red bar on the left, the difference between those two is the change in storage, which is up here. The distance in time between those two is the change in time. The inflow rate is the height of the green bar plus the blue bar. So that's inflow. And the outflow rate is the height of the green bar. So if you recall this equation from earlier in the course, that's our hydrologic mass balance equation. And all the terms are defined in this graphic. Generally, what we're interested in is we're going to know inflow. We're going to know what our time step is. We're going to hope to be able to estimate a change in storage, and we want to predict outflow. So this equation rearranged as outflow equals delta S over delta T. Equals minus delta S over delta T minus inflow is the outflow. So this cartoon is depicting what I just did in the drawing. The bar heights are related to one another through something called the routing table. And a routing table may very well be a table in a spreadsheet. More commonly, it's certain geometric properties that are supplied to your computer model that keep track of what's coming into and leaving storage. And it goes by the name of a routing table. It's a computational representation of this equation for a certain reach which has known storage properties. And we can know the storage properties by knowing the shape of the reach, if nothing else. Collectively, that's called hydrologic routing. And so the hydrologic routing techniques use that equation of continuity in some linear or curvilinear relationship between storage and discharge within the routing element to perform the calculation. So a couple of methods that are in use. One's called lag routing. We're going to examine that today, which is the whole point of introducing it now. A second type is called level pool routing. It's also called poles routing. Poles is some guy's name. And then another one is called Muskingum-Kunge, which is, I advocate it's almost a hydraulic model. It's not quite, but it's pretty darn close. And there's a few more in the hydrologic routing. And then
Hey, Dr. Cleveland?
Yes?
2 things. 1, John's in the lobby needs to be let in to the meeting.
Okay.
And 2, you're not sharing a screen.
Oh, you're kidding me. Okay. John, done. So I just went through all that and there was nothing there. Okay, cool. Let's start over and we'll do all that over again. It was not sharing at all? Okay. So let's try this all over again. But only this time I'll go faster. John and Superada have been admitted. Can you all hear me?
Yes.
Okay, excellent. So I will go back through what I was just talking about, but I'm going to go faster this time. Today I want to introduce the topic of routing, and we're going to work through 2 HEC HMS examples. And for you who just joined us, the web server is not working right today, so as of this instant in time, you're not going to be able to get these files because they're not serving correctly. And it's something I think I can fix. I'll have a solution by this afternoon of some kind. I'm hoping it's easy, because if it isn't, I'm going to be very unhappy. So routing hydrographs is the process where we're going to simulate the movement of a discharge signal through reaches. Now, reaches can be a stream or a creek or even a reservoir, like a large water storage reservoir or a water ski basin that performs additional duty for hydropower and drinking water supply, but it was really built for water skiing. Okay, that was a bad joke. Routing accounts for storage in the routing element and flow resistance, and it allows us to represent a watershed as being comprised of a collection of sub-watersheds that are interconnected through their routing elements. There's 2 kinds. One's called hydrologic, the other's hydraulic. Hydraulic routing uses continuity momentum, essentially the St. Venant equations, which are the subject of the open channel flow class. I can't remember the number right now. CE 5364, something like that. We're going to touch on it later next week, but we're not going to do it any justice that you would get out of that full class. Hydrologic routing simplifies the St. Venant equations by neglecting acceleration and inertia terms, and essentially what's left at that point is mass continuity, and that's called hydrologic routing. So the routing problem is you have a hydrograph at one location, the input, and you have some knowledge of the reach characteristics or the storage characteristics for the routing element, and it's a function of inflow, outflow, and there's going to be geometry terms. And you need the hydrograph at the outflow. That is a routing situation, and the reach can be a reservoir or a similar feature. So this diagram, which I will draw on all over again, I'm mad at myself, so that was, actually I can make better choices of color this time. So on this diagram, imagine that we have a reach. So it's some kind of hydrologic element. So I'm drawing a little rectangular channel. So there's our input flow, there's our outflow, and this reach has some kind of length. And as you see in the drawing, it has some kind of geometric features. And the amount of storage in it is going to be the cross-sectional area multiplied by the water depth at each location, added up for the entire length. So that's pretty straightforward to conceptualize. So at the inflow, this curve represents the inflow hydrograph. And I'm drawing it with this little blue wiggly line thing here. Our outflow hydrograph, which is at that downstream location, L units away, is depicted by this yellow line here. So what we have is the inflow gauging station and then the old yellow gauging station. The peak discharge at the inflow hydrograph occurs earlier in time than the peak discharge of the outflow hydrograph, and that's because the flow at that point has to transit this reach element, and that transit time is called the travel time, and it's depicted here as travel time, and it's the distance in time between the two peaks. Obviously, for a multiply peak system, that could be somewhat hard to draw. The peak discharge value, the magnitude, changes, and that's called hydrograph attenuation, and it's depicted by this vertical difference in hydrographs. The attenuation is attributed to friction along the routing element as well as storage that's going on. If we select some moment in time, this green bar plus the blue bar represents the inflow rate at that moment in time. And the green bar itself represents the outflow rate at that moment in time. The difference between the inflow and the outflow hydrograph at the moment in time minus delta T over 2 and the moment in time plus delta T over 2 are represented by the red bars. And so the change in storage is going to be the height of that red bar minus the height of that red bar. So there should be a little bit difference there. And it's divided by this time interval, delta T. And that provides the right-hand side of this expression. And if we look at that, we see that that's the hydrologic balance equation that we had earlier on in the class. If we now rearrange that equation, we're usually going to want to predict the outflow. So the outflow is equal to inflow minus delta S over delta T. That's not bad for mousing around. So usually we're going to know our inflow, and because we'll have geometric properties of the reach element, we can approximate delta S over delta T and use this to predict outflow. And in this context, this would be a hydrologic routing example because we're not considering momentum terms. This diagram pretty much depicts what I just drew. And so now we get to where we were before. So the hydrologic routing techniques use that equation of continuity I just described and some linear or curvilinear relationship between storage and discharge in the river. In other words, that delta S over delta T has to somehow be provided. And usually we use a curvilinear relationship based on the previous outflow. Essentially, we can figure out what the storage is. And that introduces several methods that can be used to route hydrographs. One is called lag routing, another is modified pools, or I call level pool routing. A third is Muskingum, Kunj, and there's a few more that are hydrologic models. In the hydraulic models, which we'll study next week, we'll be using SWIM as the computational tool. Today we're going to examine lag routing. And what lag routing is it ignores attenuation. So lag routing strictly considers just the travel time. And so lag routing will take that inflow hydrograph and lag it a certain time to correspond to the distance that it traveled. Now that's arguably an approximation. In practical sense, it's usually pretty defendable for relatively short travel distances. Short on the order of a few miles. Once we get much further than that, the storage in the element is so significant compared to the flow values that the attenuation has to be accounted for. Okay, so that was the introduction part into routing. And now I want to segue into an example. This is the Ash Creek watershed in Dallas. If you look at this shaded relief map, there's one tributary there and another tributary. I'm going to go ahead and draw those. And today the tributaries are going to be cyan. So there's a clear tributary there. There's another clear tributary there, and you might argue successfully there's a third one there. And so all that would be obtained through techniques and approaches we've discussed in the course already. And you've seen the topographic map of this same area. A digital elevation model doesn't do justice to a watershed without some sort of aerial imagery. If we were to look at this in aerial imagery, we'd see a whole lot of concrete and buildings and not a whole lot of obvious drainage channels. They're there. We don't affect the topography that much when we build a city on top of it. But they're not as obvious in either aerial imagery or a topographic map. But combined with the elevation map, we get a pretty good geometric understanding of what the watershed shape looks like. And using the tools we've already studied, it wouldn't be difficult for us to come up with a drainage area, 6.9 square miles, main channel length, and I think in this particular watershed, the main channel is defined as that. And a main channel length is not necessarily what you and I think of as a human being. It's defined by a computational scheme. So it's the distance, it's the longest path from the outlet to a point on the watershed boundary. And then the main channel slope along that path is shown here as 0.005 dimensionless, or that'd be 0.5% slope. And the curve number is 86, and that was determined independently of any metrics in this digital elevation model. And R, which is a rock factor, is 0, and that will make sense in a second. So we're going to simulate this watershed using HEC-HMS. As it's drawn here, this is not going to be a very difficult simulation, but I have a purpose, which is we're going to break that watershed later on this morning into 3 sub-watersheds, and then we'll have a routing issue. We'll have to figure out how to connect things. So to do this in HEC-HMS, we have to build a hyetograph, loss model, transform models. We've already seen those. And there's Excel sheets that have already been built to help give us the data that's required. We're going to ignore this method described here because it's obsolete. Instead, we'll put this over here. Instead, we can use either the precipitation frequency data server. I've already put it onto Dallas, and 5-year 3-hour storm is 3.10 inches, so the old method is not horribly off. And an alternative would be to use EBD lookup, or EBD USA, which can look this up for any state in the United States. Someday I'll make this work for the whole world, but it's not too hard to observe. There's an awful lot of effort that went into getting an underlying database. Go ahead and hit 3 hours, and it says, oh, I did that wrong. That was 3 minutes. We'll try that one more time. TEX County. That part's not working right. Set it to hours, set it to 3 hours, hit return, and it says 1.01 inches per hour for a 5-year. You multiply that by 3, that's 3.03. So we're looking at a depth of somewhere around 3 inches. So we'll use that value. So keep that in mind as we build our model. Next, we're going to need to create a hyetograph. And there's an online tool that may not currently be available because I think that particular server is indeed broken. And if it will ever let me get back to the calling server, there we go. Texas specific. So far so good. We need this spreadsheet here. And I can't do that on the remote, so I'll get my local copy. So you can certainly download that and run it on your machine. There should be a copy of it here. There we go. So this is not a difficult spreadsheet to use. Literally only has 3 inputs. The purpose of it is it gives us a way to generate a rainfall time series. So we'll choose the 50th percentile, because that's what the report 5075 recommends. So we have 3 hours. Our total depth is 3 inches. That's convenient. And let's get 15-minute intervals. And so that will be our hyetograph that we're going to supply to HEC-HMS. And so we now have the rainfall information. Next, we want to come up with a loss model for this Ash Creek watershed. The initial abstraction constant loss model described in the TxDOT 4193-7 report is appropriate. And there's a regression equation that allows us to estimate initial abstraction based on main channel length, the development factor, which in this case is a 1, the rock factor, which is 0, and the curve number that we determined using NRCS methods, which I can't remember what it was. Curve number was 86. And we can perform that, we can actually parameterize that equation, and we come up with an initial extraction guess of 0.567 inches. And there's a constant loss regression equation, same concept, different input values, main channel length in this case, and again the rock factor. And we now have our loss model parameters. Finally, we need transform parameters. If we were to use those gamma distribution, we would come up with a shape of about 3.4 for this particular watershed, and we will come up with the conclusion that 3.4 is close enough to 3.7. We'll just use the NRCS. But in that same report is a way to estimate time to peak based on development and channel length and channel slope, 85 minutes in this case, and then K, which is the shape value for a gamma unit hydrograph, is based on development and channel length, and we get a K of 3.2. If the K was 3.7, that would be the same as dimensionless unit hydrograph. For this example, I'm going to stipulate that 3.2 is close enough to 3.7 that I can just use the SCS without modification. And we saw yesterday, in some sense, how to insert a user-specified hydrograph. So if we wanted to stick with the 3.2, we could generate a response hydrograph independently of HEC-HMS and supply it as a unit hydrograph table. And in this case, the basin lag time is 48 minutes, and we associate lag, or the time at peak, to time of peak to the lag time. 6/10 the time to peak is conventionally used as the basin lag in the NRCS dimensionless unit hydrograph model. So now we're ready to build the HMS model. So I will switch over to our modeling environment, and let's see, how can I shrink? There we go. And so we launch the HMS software, and as an aside, I have backup files in case I fail. So let's create a new project. We're going to call this Ash Creek lesson, what are we, 15? I guess we're 16 actually. And we will put it in US customary, hit create. And now we have a base model. So we've done the creation, and we'll start to choose components. So the components we're going to need a basin model. I'm going to be lazy today and just take the defaults. We're going to need a control specifications model. We're going to need a meteorological model. And we're going to need at least time series. And I'll stop there and I'll add additional time series when we get to that point. So in our basin model, there's our basin. We were going to represent this in this first example as a single subbasin. There's our watershed right there. And now we need to parameterize it. It's 6.92, the other two, square miles. And we're going to use initial abstraction constant loss as our loss model. And I don't want to use a user specified unit graph. I want the SCS unit graph. And that's it. So that's ready to go. Let's go ahead and parameterize the loss model using the data we've already prepared, which is 0.567 and 0.381. So our initial loss is 0.567 inches. Our constant rate is 0.381. Save that. So we're partway there. The next we want is our basin lag time, which we have set at 48 minutes. So the loss and the transform have been provided. Now we're going to have to put the hyeta graph into the spreadsheet, into the program. We're going to use 15-minute intervals. So these are cumulative inches. Time interval is 15. And we will adjust the actual time window later on. For time being, we'll just run it from 1 January 2000. So there's the table. And now we need to copy that. And our usual stunt, because we're using the remote workspace. Paste it there. Copy that. Paste it here. We'll complete the input. Using the fill feature. I'm waiting on the internet to catch up with my... It's not going to work today. Hello. You gotta move, dude. So I'm trying to get the fill feature to work. And it currently doesn't want to function today. That's somewhat annoying. We definitely have a broken internet. Oh, don't put your tail there. F. This is creating input. I'm not touching a thing right now. That's a consequence of the network environment. Can we cancel that? I may have to re-enter this gauge entirely. Yep, the window manager's broken. So let's save everything. Exit, we'll restart. Have been hacked badly. Okay, the reason I'm having trouble doing data entry is there is another connection that is running my... Damn it, Dusty, your timing stinks. There's another connection that is attached, which, remember who I was blaming earlier? It's one of them. So I will attempt. Lose control of the machine is very frustrating. So let's try that all over again. All right, here we go. All over again. We're going to attempt to launch the program. If we got lucky, the saves will so it completely destroyed everything. So we'll re-enter all that. We'll see if I can get the fill feature to work. Now it's behaving nicely. Right click, choose fill. And we want to repeat the first value, which should be a 3. Graph it. Okay, that's correct. That's how the input should look like. This is cumulative precipitation. So a 3-hour storm starts at 0, and at 3 hours, there's no additional input. We'll go back to our example. So we've done all that. The only difference is we'll mess with the time window. And create rainfall, we've done that. Used a much superior meteorological model was what we will parameterize next. In this we have to include the subbasins. And our precipitation is specified hyetograph. Subbasins have been included, and we need to tell it which gauge to use. So that's our meteorological model has been parameterized. Time series is set. Basin set. For the time being, I'm going to just use the January 2000 input, and we will change it to the correct date shortly. "15-minute time interval." We're good there. And I'm going to go ahead and gamble. Hope I can get an output. So compute, create compute, simulation run. Cool. That actually ran. That almost never happens. And if you want to go look at our results, excuse me. So there's our simulation model. The red area up here is the loss model, or we consider that to be rainfall that's infiltrated and is no longer part of the signal. The blue is the excess precipitation, and then this blue curve is the simulated hyetograph of our watershed. And we can go look at this particular example. And that's not what I wanted to have happen. Oh, and it goes into disobedience mode. So here's the two simulations. They have a lot of similarity. The main difference is the use of the 15-minute interval uses versus 5 minutes in the notes. So we could use a historical storm to see how well or poorly our simulation was if we had the historical storm. And we went through how to do that yesterday, but I'll repeat it today in hopes that I can do it wrong yet a second time. So in the case of a historical storm, we'll go to the time series data manager and we add a discharge gauge. And now we have to find one. I can shrink that for the time being. I don't need that spreadsheet anymore, I hope. And we will go back to my local copy of the lesson. So here's the initial abstraction model that I use to parameterize things. Here is a rainfall model for a historical storm that was May 10/5, October 5th, 1972. So hours and rainfall. So we'll go ahead and we'll put those in a second. And then here is a flow observation expressed in cubic feet per second for that same storm. So I'm not going to change the loss model or the hydrograph model, but we will change the precipitation and discharge data and see how well our hydrograph performs for this watershed. To make that change, we need to add a precipitation gauge. And this one we will go ahead and set to the correct time, so May 1972. And so it went for, let's see, 2 days and a few hours. So it's going to go to 5, 7, I think that's the correct time window. So 5 to 6 is 1 day, 6 to 7 is 2 days, 7 to 8 is 3 days. And we'll check that the table, I think I got it right. So now comes the cut and paste. We want to cut this rain, we want to copy this rainfall. And we need to get it into cumulative inches. Oh, it might actually all work today. That's cool. Copy that. Hit paste. Go all the way to the bottom. And I'm off by 1 day. My bad. That's easy to fix right now. Go to the time window and I change that to 7. And there is our input. So that was easy. Let's go ahead and save it. And I just said the dangerous word. Whenever someone says that was easy, it means it's about to break. And now we'll go ahead and, since we actually have observations, we will incorporate those into our program. Okay, so it's a cubic feet per second, 15-minute. Time window is 05 May 1972 to 07 May 1972. And we go to 2 hours on the 7th. Should be the same time window. Looking good. And now we want to put in our our flow. Oh, it's not going to work. Don't understand that. Save it. Time series, cumulative cubic feet per second. Time window's correct. Let me save it and exit, and we'll restart the program again. Cool, that worked. All right, so now we have all our data in. Let me save it. And we will now change the meteorological model to put the correct gauge in. So now we're on gauge 2. And now in the control specifications, we have to change the time window to 5 May 1972, 7 May 1972, hour 2, 15-minute interval. We are happy. And that's set to go. And I want to go ahead and put the output. So I haven't done this in years. I have no idea what's about to happen when we put the observed flow. But I'm going to go ahead and run it and see what happens. Wow, no complaints from the computer. That's unusual. And here we see the observed and the simulated. So when you have data, one conclusion here is our loss model is terribly inadequate for this particular storm. Seems like we need a lot more loss, for instance. We could switch loss model choices because we do have the curve number for that particular watershed as 86. I'll do that. See what happens if we do that. Doesn't make much difference. There is a lot less observed runoff than simulated runoff. What is quite interesting, however, is the shape is somewhat okay. And I think I'll return back to our other loss model, which was initial abstraction, constant loss, if I can find it. Now I can't remember the values. .567.3 at 1. 0.567. 0.381. Save it. Run it. So it looks to me that the loss rate should be increased a lot. So I will knock this up to 8. Better. I'll stop fussing around. With some additional trial and error, we could get a adequate fit. Let me return to our synthetic values. Okay, so those are our synthetic values. So part of the this problem is more to learn how to, or demonstrate how to put data in and out of the program. The synthetic hydrographs, sometimes they perform better than this example right here. They don't usually perform worse. One of the desirable features is we at least capture the two hydrographs on the same plot. So if we have observations, we could start from here and then refine our model. Let me return to the presentation. I know I'm burning up time. The next step is to take this same watershed and look at it in a different structure. So this slide doesn't change. But now let's suppose that we have decided that we can break it into 3 subbasins. In this case, green, red, and blue. And the connectivity of the subbasins are that green passes through red to the outlet, and blue passes through red to the outlet. So we have 2 routing requirements. We have to route the green discharge to the outlet, and we have to route the blue discharge to the outlet. We also have to route the red discharge to the outlet, but it's directly connected. So we'll simply have a unit hydrograph for the red area that goes straight to the outlet, a unit hydrograph for the green area that enters a routing element, makes its way to the outlet, and a unit hydrograph for the blue area that routes to the outlet, and we add those 3 together at the outlet, and the composite output represents the behavior of the watershed as a whole. So the red watershed, we could look at the following approaches. We can produce a unit hydrograph for the direct part of the red outlet, so there'll be area, time of concentration, some kind of loss model. Green watershed, there'll be area, time of concentration, and loss model, and that gets us flows to this point right here. Then we're going to route from that point to the outlet, and in this example we're going to use lag routing. And then for the blue watershed, same concept. It'll have an area associated with it, some sort of time parameter, and a loss model. That gets us discharged to this point. And then that point is routed to the outlet. In this example will be lag routing. And then the 3 hydrographs that we've just produced, the red, blue, and green, are added together at the outlet, and that is declared the composite outflow hydrograph for the entire watershed. So to prepare the model, I'll get started today. We're not going to finish because I only got about 10 minutes of your time left, and I need to honor that. But I think I want to stick with this particular setup here because in my mind the hard work's already done. So I'm going to return to my basin model. And so we're going to need 3 basins. So I'm going to go ahead and create the red basin. Create the green basin. Create the blue basin. I'm going to create something called this. Yeah, I'm going to create a sink. So sink is an element where everything's going to just go to. This is a mostly a modeling trick. Go composite. And I'm going to delete subbasin 1. No, actually I won't. I'm going to leave subbasin 1 alone. Here's another cool modeling trick. We can have the appearance of two different models on the same drawing canvas, and it gives us a way to compare the two. So our setup is, let's see, it's red, blue, and green. Roughly that topology. And remember, this is drawing. The actual relationship relative to the picture is irrelevant as we have it. All right. So that's our initial setup. And so the next thing would be to prepare a base map, the drawings, and make the measurements. We know the total area is 6.92. And this just shows you how to make measurements. So I come up with red watershed's 1.87 square miles. So we'll go ahead and enter that. 1.87. Green watershed is 2.67. Blue watershed's 2.39. Now we need some distances. So the distance from the Green watershed outlet to the Ash Creek watershed outlet's 4,227 feet. We're going to need that later. I haven't drawn the elements. And so what we're next going to do is introduce reach elements. Reach 1 is going to be green to outlet. It's not behaving right. I know I've created a reach. Okay, so the downstream connection is composite. Routing method will be lag. Choose the okie dokie, and now the green thing exists. We connect green to outlet. And now we have the connection displayed. So we'll do the same for another reach element. This is going to be blue to outlet. Get the creation. That's weird. Blue outlet downstream connects to the composite. Routing method will be lag. Choose OK. Blue goes to blue to outlet. Yes, cat. Be with you in a minute. Hi, guy. And I will continue this example for a few minutes tomorrow, and then we're going to look at level pool routing. So thank you for your attention. Sorry if today seemed kind of discombobulated, but having the web server misbehaving sort of threw me for a loop, and I will get on getting that diagnosed and repaired quickly. So if there's no further questions, I want to thank whomever told me that I was babbling away without sharing the screen. Looks like the recorder's on, so all of what I've done will be recorded and preserved and uploaded. And I will see you tomorrow at the same time. And what we're looking forward to for your next exercise is I will provide sufficient information to build a Heck HMS model, actually very much like what we're doing right now, to experiment with and give you some practical experience to using the tool and applying hydrologic principles. So with that, if there's no questions, I'm going to go ahead and end the meeting. Does anyone have questions? I'll wait a few seconds before you have a chance to unmute yourself. All right, very good. Well, I'm actually going to complete this problem. Probably I'll do it recorded and just add it to the end of the video, and then I'm going to go ahead and diagnose the problems with the web server. So very good. Have a great afternoon, and I will do my best to get the internet stuff working again. And I totally hope it's in my hands and it's something I screwed up, because if it is out of my hands, I don't really have a fallback that I usually do. So I'll see you tomorrow, and if there's any change in that, I'll send a group email out. In the meantime, again, have a great afternoon. Bye-bye. All right, to complete the setup for this example, I've created the two reach elements, and all I'm doing right now is fussing with the drawing. I've connected the green to the green outlet element, so that's what this black line represents, and then the thick blue line represents the reach element. I've done the same with the blue watershed. Blue to the outlet, and then it's taking the thick line to the outlet. Composites, where we're going to collect all the hydrographs. And then the red directly connects to the outlet. And we will pick up with this example tomorrow. Remember, subbasin 1 is Ash Creek single basin. If it lets me update, I'm going to go ahead and change its name. I think you used to be able to rename it. Oh, I guess I can't rename it. Cancel that. Can rename it over here. So we'll call that one Ash Creek Hole Basin. Very good. Let me save this, and we will resume this tomorrow.